This is Hugging Face, Deep RL course, Unit 4. Diving deeper into policy gradient, getting the big picture. We just learned that policy gradient methods aim to find parameters theta that maximize the expected return. The idea is that we have a parameterized stochastic policy. In our case, a neural network outputs a probability distribution over actions. The probability of taking each action is also called action preference. If we take the example of cartpool V1, as input we have a state. As output we have a probability distribution over actions at that state. So we have a diagram here. There's some attributes: position, velocity, pole angle, pole angular velocity. And we have, an input layer going into a fully connected layer with this policy parameterized by theta, and then a softmax, which gives us the probability distribution over some options, and the options here are push left and push right. Great. Our goal of policy gradient is to control the probability distribution of actions by tuning the policy such that good actions that maximize returns are sampled more frequently in the future. Each time the agent interacts with the environment, we tweak the parameters such that good actions will be sampled more likely in the future. So this parameters theta is what we want to change to make sure good actions happen. But how are we going to optimize the weights using the expected return? The idea is that we're going to let the agent interact during an episode. And if we win the episode, we consider that each action taken was good and must be more sampled in the future since they led to the win. So for each state action pair, we want to increase the probability of this action given the state, the probability of taking that action at that state, or decrease it if we lost. The policy gradient algorithm simplified looks like this. Policy gradient, we have a training loop, and in that loop we collect an episode with pi, calculate the return, sum of rewards, and then we update the weights of pi. If positive return, increase the probability of each state action pair taken during the episode. If negative, do the opposite, decrease the probability. Now that we got the big picture, let's dive deeper into policy gradient methods. Alright, let's look. Diving deeper into policy gradient methods. We have our stochastic policy pi, which has parameters theta. This pi, given a state, outputs a probability distribution over actions. Okay, we've seen this. Where, pi of action given the state is the probability of an agent selecting an action from a state given our policy. But how do we know if our policy is good? We need to have a way to measure it, to know that we define a score or objective function called j, parameterized by theta, right? So the objective function gives us the performance of the agent given a trajectory, state action sequence without considering reward, contrary to an episode, and it outputs the expected cumulative reward. Okay, so let's look at this objective function. We have this j, theta, and it equals this e and expectation of maybe this policy and this reward at this trajectory tau, read tau. So this reward of tau is the cumulative reward, and it's this reward at each time step t plus 1, t plus 2, t plus 3, t plus 4, discounted by gamma, which is our discount rate. Okay, let's go to, let's detail a little bit more about this formula. The expected return, also called expected cumulative reward, is the weighted average, where the weights are given by p of tau theta, of all possible values that the return r of tau can take. So here's an objective function. Here's this j, here's the sum, and it's a weighted average. We calculate the expected return j by summing for all trajectories the probability of taking that trajectory given parameter and the return of this trajectory. Probability of the trajectory depends on theta, since it defines the policy that it uses to select the actions of the trajectory, which is an impact of the states visited, and then the cumulative return from trajectory. This is r that we saw above over here. So R is its return from an arbitrary trajectory. To take this quantity and use it to calculate the expected return, we need to multiply it by the probability of each possible trajectory. Here this P, probability of each possible trajectory, tau. That probability depends on theta, since it defines the policy that it uses to select the actions of the trajectory which has an impact of the states visited. Alright, so here's this objective function, and here's the objective function spelled out a little bit more with this p-value, this probability value is expanded. So here, this p is made up of these environment dynamics. So these are the state distributions times the probability of taking that action A at states t. So J, as we know before, is expected return. Calculate it by summing, for all trajectories, the probability of taking that trajectory given theta and the return of this trajectory. Our objective then is to maximize the expected cumulative reward by finding theta that will output the best action probability distributions. Alright. So we want to maximize the objective function where we maximize J, where the goal is to find the weights theta that maximize the expected return. We're always trying to maximize this expected return, and in this situation what we can change is theta, these parameters. So gradient ascent and the policy gradient theorem. Policy gradient is an optimization problem. We want to find the values of theta that maximize our objective function J. We need to use gradient ascent. It's an inverse of gradient descent since it gives a direction of the steepest increase of J, and J is expected cumulative reward. So I guess that's what we want to increase. If you need a refresher between gradient descent and descent, check this and this. Okay. So hope this is not another 1 hour video. What is the difference between gradient descent and ascent? In this tutorial, we'll study the difference. I'll leave this as an exercise for the reader. But hopefully they're roughly the same, where one is a min function and one is a max function. The update step for gradient descent is this. Theta at any point, theta changes at the learning rate times this change of the parameters times J. We can repeatedly apply this update state in the hope that parameters converges to the value that maximizes J. However, we have two problems to obtain the derivative of J. We can't, so problem number one, we can't calculate the true gradient of the objective function since it would imply calculating the probability of each possible trajectory, which is computationally super expensive. We want then to calculate a gradient estimation with a sample-based estimate. So we collect some trajectories. Problem number two, we have another problem that I detail in the next optional section. To differentiate this objective function, we need to differentiate the state distribution, called Markov decision process dynamics. This is attached to the environment. It gives us the probability of the environment going to the next state, given the current state and the action taken by the agent. The problem is that we can't differentiate it because we might not know about it. Okay, we'll see that in the next section for more explanation. But we have these two problems. One is we must sample. And two, it seems like we might not know these probabilities. Okay, this, I believe this is the same slide. Fortunately, we're going to use a solution called the policy gradient theorem that will help us to reformulate the objective function into a differentiable function that does not involve the differentiation of the state distribution. Okay, great, we have a fix. The policy gradient theorem. For any differentiable policy and for any policy objective function, the policy gradient is this. It's good to know that we have one. If you want to understand how we derivate this formula that we will use to approximate the gradient, check out the next optional section. Okay. The reinforced algorithm. The reinforced algorithm, also called the Monte Carlo policy gradient, is a policy gradient algorithm that uses an estimated return from an entire episode to update the policy parameter theta. In a loop, we use the policy pi to collect an episode tau, and then we use the episode to estimate the gradient. Awesome. So the policy gradient in one trajectory. This is an estimation of the gradient. Probability of the agent to select the action from state S at t given our policy, and this is the direction of the steepest increase of the log probability of selecting action at state, or at action A at t from state t. So then we update the weights of the policy. Great. By this estimation instead. The interpretation we can make is this one. This delta log, upside down delta log pi, is the direction of steepest increase of the log probability of selecting action A from state S. This tells us how we should change the weights of policy if we want to increase or decrease the log probability of selecting action A at state S. So this R at tau is the scoring function. If the return is high, it will push up the probabilities of the state action combinations. Else, if the return is low, it will push down the probabilities of the state action combinations. We can also collect multiple episodes or trajectories to estimate the gradient. Awesome. So we have the estimation of the gradient. Given we use some trajectories to estimate the gradient, we have the scaling factor to inversely proportional to the number of trajectories. And then we have this probability of the agent. Here's the probability. And we have that at log probabilities. And this is the cumulative return of the ith trajectory. Awesome. Thank you for sticking around. Enjoy.